Hello, welcome to this video. This is a fairly impromptu video. If the recording doesn't go too well, I'll probably make another one. But I realise I haven't provided a video for the channel for a while. A lot of that is to do with moving, with my parents being in Southend, and soon I'll be moving to Southend. So there's all of that going on. But I have been keeping an eye on the channel. It'd be good to make a video to explore another concept. So last time we looked at subshells of electrons and atoms, which aren't really talked about in A-level chemistry, and why it's sometimes said that they don't even necessarily exist, at least for stable atoms and their ground states. Today we'll be looking at another thing in quantum mechanics, but something a bit more general. And that is we'll be looking at the wave function. So if you've seen some of my videos, the wave function is a mathematical description we use to express an object when it is in many different available classical states at the same time. For example, when a particle is in many places at once and thus displays some wave-like properties, because a wave can be in many places at once. So the wave function is kind of core to quantum mechanics, and what happens according to standard quantum mechanics when we make a measurement is we go from this object being in many classical states at the same time, where we say the object is in a superposition classical states, to the object being in a single classical state, and lots of different interpretations of quantum mechanics is going, what happens here? Why does the wave function collapse? Is the wave function really collapsing, or is something else going on? Or should we even metaphysically ask the question, what happens during measurement, and should we only just care about what we measure and thus treat quantum mechanics as a computation device? So there's lots of things going around the collapse of the wave function in quantum mechanics, lots of discussion, and to help you explore that discussion if you would like to, I thought it'd be good to do a video on the wave function itself and why we use complex numbers to represent the wave function, particularly given that if you represent the classical wave, you could use complex numbers if you like, but you don't necessarily have to. So why in quantum mechanics do we use complex numbers to represent the wave function? Well, for this, I would like to kind of look at two aspects of the wave function which complex numbers naturally have built into them, thus making complex numbers a good kind of input into our wave function when we're dealing with a quantum mechanical wave function. So firstly, we would like our wave function to be able to describe or have built into it something that I've called relative amplitude. And by this I mean that we would like to be able to represent a wave function as being closer to one classical state than another, let's say closer to classical state A than B, if when we measure a particle in that quantum state, we are more likely to find the wave function collapses to state A than state B. So we want some notion of a wave function being closer to one of its input classical states than to another classical state. And this is where the idea of relative amplitude comes in. So if we look at our diagram on the left and right, we've got a red arrow, and I'm using the red arrow to represent a quantum state. And Y and X are my classical states. Now you'll see in the diagram to the left the red arrow is closer to classical state Y than X. And by that I mean if we were going to project our red quantum state onto Y and X, we would see that a greater amplitude of the wave function lies along Y than X. So we would say our red arrow has a greater relative amplitude in Y than X, or it has a bigger projection on Y than X. Whereas if we look at the diagram on the right, we can see that the red arrow is orientated closer to our classical state X, and that would mean that if we were going to measure a particle in a quantum state described by our red arrow, we would be more likely to find it in classical state X than Y. And so we can see that by changing the orientation of our red arrow relative to classical states Y and X, we actually change the quantum state and change what our quantum state is telling us. For example, if our red arrow was at 45 degrees to both the horizontal and vertical axis, then that would be telling us that if our particle is in that quantum state, then we are equally likely to find it in classical state X as in Y. And so essentially we can summarize this more formally, and we can say if we look at acute angles, so angles less than 90 degrees, going anti-clockwise from the X vector, then the greater the angle, the greater the projection of the quantum state or red vector onto classical state Y than classical state X. And so we would like to have numbers which have built into them this idea of relative amplitude, and thus have built into them the idea of some kind of angle between the classical states and our quantum state. So we want a number which has some idea of angle and relative amplitude to enter into our description of the wave function for our quantum mechanical state. And the second thing we would like our wave function to be able to describe, as well as relative amplitude, is something called normalization. Or at least we would like to be able to normalize our quantum state and our wave function. Now, normalization is a property of any theory that deals with probability. But specifically in terms of classical physics, so when we've got our object in a quantum state, when observed, standard quantum mechanics presumes its wave function is the sum of all possible classical states of that variable. So, like if we've got a particle, our particle before observation is in one particular place, is actually in many, many places at once, and thus has some wave-like properties. The moment it's observed, or at least we observe where the particle is, the wave function collapses and the particle ends up existing at some location. But if we sum the probabilities of the particle existing at one location to another location, and another location, and another location, and we sum all the probabilities, we should get 1. That is, we should be certain that when we measure where the particle is, the particle does end up existing at a single point in space. We might not know where that place will be, but we should be certain that it ends up existing somewhere. Or to put more formally, the total probability associated with our wave function should equal the probability of our particle collapsing into any one of the possible classical states, and this total probability, should equal 1. That is, it should definitely, for certain, with 100% certainty, collapse into one of its classical states. And so we need some notion of some notion of a scalar variable, i.e. not something with direction. We want an idea of a scalar variable, where the scalar variable would tell us about the probability contained within the wave function. So to summarize, we need our wave function to take in numbers which have angles naturally built into them, but also where we can take that number and say something about its size, or something about the output of the function that we put that number into, at least the size of the output. And so because we want size and angle, we don't want to use real numbers because they just give us a size. They don't really give us much flexibility with angle. We actually want to use complex numbers because complex numbers have size and angle built into them. For example, if you look at this diagram, we have something called an Argand diagram, where you have the real component of the number on the x-axis and the imaginary component on the y-axis. And a complex number is a sum of its real part and its imaginary part. But because it's a real and imaginary part on different axes, when you plot a complex number, you actually say something about kind of the angle between the factor that represents the complex number, as well as the size of this arrow, so how big the complex number is. So that is why we use complex numbers when we're talking about wave functions for quantum objects. Now, I hope you've liked this video. This video has been fairly brief compared to the last one. It has been a lot more impromptu, but I hope it's good enough to at least keep the channel fairly afloat, give you something to learn about, and I look forward to seeing you for another video soon. And thank you very much for watching.